is W.B.Langdon, talking about genetic improvement programming.
Hi, good morning. Before I start, there's some copies of two papers here and over the side, which I'm going to refer to, but if you'd like to take a copy, then you'd be very welcome. So I'm W.B.Langdon. I'm here at the press group in UCL, and what I'm really going to be talking about is using GP to improve programs. The first paper I talked about is the work on GZIP, which mostly I'm going to skip over, and I'm going to concentrate on the second of our three examples, which has been accepted by the IEEE transactions on EC, but is yet to appear. And then, so I'll concentrate on that, and then hopefully be time for discussion at the end. So as with yesterday, shout at me if you want to raise a question halfway through. You'd be more than welcome. The idea is what we want to do is take a non-trivial system and improve it using GP. The system I've chosen is a state-of-the-art DNA lookup program. It's Bowtie 2, which is about 50,000 lines of code. So it's not a huge system, and it's written by a single author. What we're going to do is take that, which is a generic tool written in C++, and specialize it using GP for a particular task, which is processing next generation DNA sequences from the 1000 Genome Project. The nice thing about this is we have the existing program, so we have a ground truth in the sense that we know what the existing program does. In fact, we actually have a way of ranking the answers that that program produces. So we have an independent second test, which is not necessarily always true. But in this case we do. What we do is we run GP, we allow it to bloat, in fact we encourage it to bloat. At the end of the GP run we have a bloated system which we then clean up. So the last process is actually knocking out changes which are unnecessary. So there were some questions about bloat yesterday. I'm going to skip past last. So Bowtie 2, when it was published in Nature Methods, in the first 12 months, it got more than 1,000 citations. So this really is a very heavily used bioinformatics tool. As I say, it's the state-of-the-art, written by Ben Langmead. Basically, it's his PhD thesis. What we're going to do is we're going to allow GP to modify the source code, but not the header files. So you can see that there are 67 header files which the GP doesn't change, but there are 50 source files which the GP is able to change. And as I said, we take the data from the 1000 Genome Project, which is basically put all their stuff online on GP sites. So and the basic approach is we take the source code and we convert it into grammar. But this is a grammar which is very specific. It basically allows GP to both modify and instrument Bowtie 2, but it's not generic. It's very specific to Bowtie 2. And what GP manipulates, the things the GP individuals are patches to that grammar. So although we've got 50,000 lines of code to play with, what GP is evolving is small changes to the grammar. The nice thing about the grammar is it ensures that the code that comes out that's modified by GP is syntactically correct in the sense of it always has semicolons where it ought to, all the curly brackets match up, but it doesn't guarantee that the code is going to compile. overwhelmingly the most likely reason for things not to compile is simply variables going over scope.
Bill, how
Yeah.
prevalent is that? How many?
There'll be some figures later, but I'll come back to that. So the general idea is we adapt the GP, well, the normal evolutionary cycle. So the stuff in red to the side here is the original system, so the original code and test cases from the 1000 Genome Project. We create our grammar, and the thing that the GP is acting on is patches to the grammar. So we have a population of patches. We can mutate those patches. We can cross them over, and then we apply effectively reverse the grammar in order to create new source code. We try and compile it. If it compiles, we run it on data from the 1000 Genome Project, and we compare its performance with the original code. So if it's better, then the new version may come into the population. The selection is very straightforward. We sort our population and we take the top half. People in the top half get 2 jobs. So this is the top part here in red is the original source code. The conversion to grammar is very straightforward. So although we have a huge grammar, it's very simple. So almost all, well, grammars fall into 2 parts. There's this, which essentially is the name of the source file where the code came from, and the line number. So each line of the original source code ends up with at least 1 line of grammar. And the stuff I've got here in green is instrumentation. So that's been automatically added by using the grammar. And we have a simple convention that if a rule starts with an underscore, it's something that GP can manipulate. And we can replace any rule that starts with an underscore with another rule that starts with an underscore, and we'll get something that's syntactically valid. And as I've said, it may not compile, but at least the semicolons will be in the right place. So in addition to the straight assignments, there are also So,
could you just go back just for a sec?
Yeah.
How do you ensure that the semicolons fall into place? Because if you are replacing the code in red on a rule that begins with an underline, you could put anything in there.
So the code in red is the original source code.
That's right.
So the assumption is that you're taking something that compiles.
Absolutely.
And you're breaking it into lines.
Yeah.
If I substitute, there is an example later, but if I substitute that one there from that one there, they both have a semicolon at the end of the line.
They do. But so that I understand with swapping, I understand, but about creating a new one, your grammar is not forcing. It's not specifying the syntax that a line needs to terminate with a semicolon.
No, it's taking that from the original source code. So the assumption is the original source code compiled is syntactically correct. All I'm doing is taking a line and moving it elsewhere.
Yeah. But then it will work if you're swapping lines, right?
No.
But if you create a new line, you do not know that the syntax specifies that you need a semicolon at the end.
Yeah,
I'm not creating new code.
You don't need to. You don't need to. In C++, the syntax is such. There are places you can put semicolons. You're not supposed to. By doing what you just said.
Yeah. But so this grammar is not generic. It doesn't specify every C++ program.
Absolutely.
What it does is specify the variants that GP can come up with, the variants of Bowtie 2 that it can come up with.
Okay. Well, we can talk about this later.
So my mutation operator is to move things around in this grammar.
Okay.
So there's a mutation. So I can take out a line, and it will be syntactically correct. I can insert, and I can replace.
But reinserting from the existing lines and basically taking an existing line and inserting it somewhere else. That's what you mean by inserting.
Yes.
So you never create a new code ever.
Yes, exactly.
Okay.
Yeah.
Okay.
So I should credit Wes, because this is very much based on his approach with bug fixing. So what we're doing is we're manipulating existing code. We never create new code. So in addition to the straightforward assignments, the grammar recognizes if, for loops, whiles, and else. In the case of if, so there are 2,000 if statements in Bowtie 2, which GP can manipulate. And so the idea is, again, the green is instrumentation. What the grammar recognizes is the conditional part, the predicate in the if, and we can replace the predicate from this if with another predicate from any other if, and again it will be syntactic.
So the answer to both of our questions is they're forcing curly brackets, which means it's always going to be syntactically correct.
Yeah, no, I see. Like by forcing the context, yeah, that's fine. It was just the actual creation of code I wasn't seeing happen.
Yeah. Yeah, sorry, I should have made that clear. We're not creating code. We're rearranging the existing code.
Mm-hmm.
So as I said, what GP is manipulating is patches, lists of mutations. So we have an append. The way the crossover works is it appends lists together. So it's guaranteed to bloat. And the argument I had there was, well, we've got 50,000 lines of code. We're going to need to change a lot of those. Even if we start with small things. Let's encourage bloat, which is certainly what that crossover achieves. The three types of mutation, which is essentially to delete a line, replace a line with another line from somewhere else in Bowtie 2, and insert a line from Bowtie 2 in front of another one. So those are our three mutation operations. So here we have a very quick example of mutation. So again, red is the original source code. In blue is our mutation operator. So what this says is, again, this is the source, the name of the source file, line 707, and we replace line 707 with line 365. And in a GP individual, it will just be a list of these things. So it's a variable length list. And there you can see that the net effect of this mutation is, here's our original source code plus instrumentation, and here's the output. So having done that mutation, we'll now try and recompile this particular source file.
So
again,
if I understand correctly, you could almost use the original code and just swap lines around, and the only reason you have the grammar there is to give somewhat of a type to the lines, as in, okay, if I have a specific while, I can't put that on certain spaces, so it is to set up some sort of a typing in effect,
yes,
right?
Yeah. So essentially it controls what GP can do.
Mm-hmm.
So using the instrumentation, what I've got here is a count for each line of Bowtie 2 on a fairly large example where so going across the bottom is just the lines of Bowtie 2 arranged, I think, alphabetically. And going upwards is the number of times that line of code was executed. And you can see immediately there's an awful lot of white space. So these are lines of bow tie 2 that were instrumented but were never run in the cases we care about. So it doesn't mean to say they are never used, but they're not used in the cases that we're going to try and optimize for. Then there are lines of code which are used just once, and what really dominates this picture is lines of code that are used a vast number of times. So there are 2 lines of code there which are used more than 1 billion times in this particular test case. And the argument was very much, well, there's no point getting GP to modify lines of code which are never used. What we want to do is target lines of code that are used a great deal. So again, from that data, we can see that there are a variety of ways in which the usage of code varies. The easiest one is the line in red at the top, which is an example line which I've chosen for illustrative purposes, which essentially says this line of code is used almost 200 million times every time bow tie is run, regardless of what either the input or the output from bow tie 2. And it makes sense because it's a line of code in the initialization of bow tie 2 which reads in the human genome. And every time you run bow tie 2, you're going to need a copy of the human genome. So every time it's run, it goes through approximately 200 million times that line of code is used. And then in different colors, we've got different forms of scaling. So there's here again is an illustrative example where the number of times the line of code is used scales linearly with the size of the output. There's blue is the lines, an example line which scales quadratically, and in green there's an example which scales cubically. So some of these are inside nested loops, and that's why it scales in that way. So the argument was, what we want to do is get GP to target lines of code that are used a great deal, lines of code that are scaled badly. And so we devised a weighting scheme which essentially gives those lines a high probability of being mutated. So this table, going down this side of the table is the number of lines of code. So we start off with the original bow tie 2 at 50,000 lines of code by simply concentrating on the source files rather than the class headers, by excluding code which is there, conditionally compiled code which is there principally as debugging aids and so on. We reduce that down to 20,000. So that already gives us a factor of 2. By excluding lines of code which are not used in the cases we care about, we're already down to just under 3,000. The weighting scheme targets heavily used lines. Oh, thank you. Oops. No, this hasn't got it right. Thank you. And of those almost 3,000 lines, the GP actually modifies 39. 39's scattered over 6 source files. So that's the result of the evolution. And then there's this deterministic cleanup phase right at the end, which reduces our 39 modified lines down to just 7. And those 7 lines of code give us a factor of 70 improvement in bow tie speed. Yes, sir.
Puzzled about one thing, which is why. So, in the code that I've ever tried to optimize, typically it's not the line that's used a lot that needs to be working. It's closely related lines. For example, you might need to refold some loops. So I'm kind of surprised that it's targeting high usage rather than targeting being near high usage.
Well, okay, so what it's actually doing is targeting high usage. There is, yeah, I mean, it's a heuristic, and I'm quite confident that there are improvements can be made to the system. Maybe, I don't know, adding a window that's either side of a highly used line would also be a useful approach, but it's not something I'm trying to. So yeah, this is what we did and how it worked. But I'm confident there are improvements that could be made. Yeah.
Well, it kind of depends on the characteristics of the program. Some are like the ones you described, and some are like the ones Bill described. So it's part of the optimization process to figure out what sort of program you've got.
Is it a hard heuristic or a soft one? In other words, the stuff that's nearby that you're not targeting will never be.
No. So the okay. The hard part of the heuristic is lines that are never come up as being used will not be mutated. Then this is a set of weights which target heavily used lines, but there is still a chance of other lines being mutated. Yep.
Can I ask, would your system change its focus if it found that particular heuristic wasn't working well, or is it simply focused on that?
No, it's not as clever as that. The heuristic is as I describe it, and if the heuristic doesn't work, then that means I have to recode.
Well, or you can apply the system to itself.
The system's not written in C++.
What's that?
The system's not written in C++. I'm not sure you want to know what the system's written in.
I think we should be applying these things to ourselves at some point. That ought to be a goal. It shouldn't be a joke, right? It should be a goal.
But then it will only speed up the fact that it will run quicker and still not find any optimization.
Well, at least we'll understand. One of the problems we have is when it suggests changes, because we don't know bow tie, we don't really quite know why it's improving it. But at least if it's applying to the code we've written, then.
Can I ask about headers as well? Sometimes you get quite important code in headers. Have you looked into doing headers, or is that just a sort of a convenient way of chopping them into the code?
Okay, so a detail that I've glossed over is what we're doing is we're changing executable code. We're not changing function headers. We're not changing declarations, and the system could change the body of methods, but for convenience, it simply ignores .h files at present. But no, it could modify code, executable code within the H files as well. That would be possible.
I do see programmers say that you should never define macros. It should all be in line this, that, and the other. But in reality, it do.
Yeah.
So if you ignore header files, is bowtie a typical C++ program or a very untypical, more C-like program? Because I have seen many C++ programs that have just a few lines left in the actual C++ file. Everything else is in the header file. Have you looked at that? How much executable code do you have actually in the header files?
It varies a great deal. So although we've got 106 source files, they're very different lengths. So some of the .h files simply have declarations in them, and they're quite short. Some of them have very.
Perhaps we could.
Okay. Just to finish. Some of the class files have a fair amount of executable, but overall, most of the executable code is in the .c complete. Yeah, so we modify the code, we run make, we're using GCC pre-compiled headers, and we don't try and optimize. So this is all to try and reduce the time spent in compilation. Assuming the mutant compiles, we try and run it on a small number of test cases, and each generation we take the best patch, the best half of the population, and create new children from it. So the fitness is multi-objective. Do you compile? No, you don't get any children. We run, if it compiles, we run it on 5 examples, and essentially what we do is sort the population, and we sort it by the number of times the program ran, did it time out, did it segfault during the runtime. The next thing we sort on is the quality of the output. So we have this Smith-Waterman algorithm, which is a deterministic and hence slow, but it gives you what is recognized to be the correct answer. It's too slow to be used on the whole problem, but it's fast enough to use to check answers once you've got the answer. And the last thing that we sort on, the least important in the sort order, is the thing we're actually trying to optimize, which is the number of lines of code executed. So we're operating on the number of lines rather as a proxy for runtime, but we're counting number of lines so that we have a deterministic fitness. So if we run the same individual again, we'll get the same fitness value. It's not necessarily true if we were using CPU time directly. So Lee asked earlier about compilation. What we've done is we've taken a heuristic which says instead of allowing GP to move code at random, we allow it to move code at random only within the same source file. And that increased the fraction of programs that compile by a factor of about 3. During evolution, so this is GP operations on fit individuals rather than at random, about 3/4 of the time the programs compile. If it compiles, it's very likely to run and give us a fitness value. So those that fail at runtime, about 3% fail with a segmentation error, and about 2% run into a CPU time limit. And then there are a small number of other things. So about 2/3 of our population runs and gives us a fitness value. So we run with a tiny population for 200 generations, half the time using crossover, half the time using mutation, and we change our test cases every generation. And that took about just over a day. As I've said, we deliberately allowed the GP to bloat, thinking we were going to need to change lots of code. And then took a deterministic process where we essentially knock out one mutation from our list and see, does that make the GP, does that make Bowtie 2 worse? If it does, we stick it back in again. If it didn't make any difference, we leave it out. And that reduced us from 39 changes down to just 7. And these are the 7. So the top one is we're doing a replace on the I/O module, and that's the line 622 I showed you before. 4.2 means it's the center part of the C++ for loop. The original code tested the loop control variable against this variable, which in our case has a value of about 200 million. So in the normal course of events, Bowtie 2 goes around that loop 200 million times. GP replaced it with this thing, which has a normal value of 84. So we've dropped 200 million times around the loop. And you look at the loop, you can see that it wasn't actually doing anything useful. And The next three mutations are the same sort of thing. GP is manipulating a loop which wasn't doing anything useful. Those three can be treated more or less separately. These four really have to be thought of together. And what GP is doing is manipulating the Intel SIMD vector instruction set in an entirely non-obvious fashion. I've never coded the SIMD vector instruction set. I have spent some time trying to analyze that, and if people care, there's the results of my analysis in the paper. But essentially, a large fraction of the speed up comes from these, and also a large fraction comes from these four. Do you want me to stop?
I'm really informing you about our time.
I think we're running into discussion time.
We have had quite a bit of discussion, so I'm...
Okay, so we have applied these 7 changes, and the code runs 70 times faster. So what I did was to take 200 test cases from the same machine, but different individuals. So this is DNA that the GP has never seen. We take our patches, we apply them to Bowtie 2, we compile with all the optimizations that are in the release kit, and we run it. And it takes just under 4 hours. If we take the release code with all the optimization switches on, and we run it on those 200 examples, it took more than 12 days. In terms of the output that comes from Bowtie 2, 89% of the cases, the output is identical. In 9% of the cases, the output is not identical, but it's actually slightly better. A median improvement of 0.1 is not a huge improvement, but it's definitely an improvement. 0.5% of the cases, it produced a different answer with identical quality, and in 1.5% of the cases, it produced an answer which is very slightly worse. Right, so skipping on. Okay. So to conclude, this is an example where GP has taken a state-of-the-art C++ system, made small changes to it, and given us a very large speed up. There are some other examples where we've looked at some code from the gzip, the Unix gzip compression routine, and more recently looking at speeding up some legacy CUDA code. And I'm way over time. Right, thank you.